Picture the sky not with one sun, but with two. Imagine two brilliant stars hanging in the heavens, casting double shadows and painting the landscape with an alien, golden light. This isn't just a scene from a science fiction film, a vision of a galaxy far, far away. It's a cosmic reality in many parts of our universe, a binary star system. But what if that breathtaking vista wasn't just the stuff of fantasy? What if our own world, the familiar Earth we call home, once basked in the glow of twin suns? It's a staggering thought, one that challenges the very foundation of our planet's history and our place in the cosmos. This isn't merely a flight of fancy. It's a serious scientific possibility emerging from the frontiers of modern astronomy, a theory that connects ancient human legends with revolutionary new ideas about our solar system's turbulent past. The possibility that Earth was once part of a binary star system is a concept so profound it reshapes our understanding of everything from the formation of our planet to the very conditions that allowed life to blossom. We're about to embark on a journey to explore this incredible idea, a journey that will take us from the cutting-edge models of astrophysicists to the dusty pages of ancient myths, where stories of a second sun have persisted across cultures for millennia. What if those myths weren't just allegories or mistakes, but faint, distorted memories of a real astronomical event? What if our solar system's quiet, orderly arrangement is the calm after a much more dramatic and chaotic stellar storm? We will investigate the compelling evidence that suggests our sun might have once had a companion, a twin star that dramatically influenced the architecture of our planetary neighborhood before vanishing into the depths of space. This is more than just a story about stars. It's a story about us. It's a quest to uncover the deepest secrets of our own cosmic backyard, a narrative that touches on human curiosity, our innate drive to understand where we came from, and our relentless pursuit of knowledge in the face of the universe's grandest mysteries. As we piece together the clues from orbital dynamics, computer simulations, and the fossilized record of our own planet, a new, breathtaking picture of Earth's infancy begins to emerge. So prepare to have everything you thought you knew about our solar system's past turned upside down. The story of a binary Earth is a tale of cosmic wonder, a thrilling scientific detective story, and it's one that promises to change the way you look at the sky above you forever. To understand just how radical this binary star idea truly is, we first need to revisit the story we all think we know, the standard textbook model of our solar system's birth. For centuries, astronomers have pieced together a narrative that is elegant in its simplicity and powerful in its explanatory scope. It begins with a vast, cold, and lonely cloud of interstellar gas and dust, a silent nebula drifting through one of the Milky Way's spiral arms. Then something happens, perhaps the shockwave from a nearby supernova, or simply the slow, relentless pull of its own gravity. This cloud begins to collapse. As it contracts, it spins faster and flattens into a whirling disk, a cosmic carousel with a growing, dense, and hot protostar at its very center. This is the nebula hypothesis, the foundation for everything we understand about our celestial neighborhood. From this spinning disk, the planets themselves begin to coalesce. Closer to the fiery new sun, where temperatures are scorching, only metals and rocky materials can survive, clumping together to form the inner terrestrial planets, Mercury, Venus, Earth, and Mars. Farther out, beyond what's called the frost line, it's cold enough for ices to exist alongside gas, allowing the cores of the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune to rapidly snowball in size, sweeping up vast atmospheres. What emerges from this chaotic infancy is a system of remarkable stability and order. A single, middle-aged, and utterly predictable star anchors it all. The planets, including our own Earth, follow nearly circular, well-behaved elliptical orbits in roughly the same plane, a clockwork harmony that has persisted for billions of years. This is the solar system we're taught in school, the one we see depicted in planetariums and documentaries. It's a system defined by its solitude and its singular light source. Our sun, for all its power, is a lone star. This picture of peaceful, solitary order is what makes the notion of a second sun so jarring. It challenges the very premise of our planet's quiet, isolated cradle. When we hold up this established, comforting story of a lone star and its neatly arranged planetary family against the possibility of a turbulent, binary past, the contrast couldn't be starker. One is a tale of serene, gradual formation. The other hints at a far more dramatic and dynamic childhood for our world, a history written not by one star but by two. But while the idea of a second sun in Earth's sky might sound like pure fantasy, the truth is that multiple star systems are not the exception in our universe, they are the norm. In fact, solitary stars like our sun are in the minority. When we look out across the Milky Way, we find that most stars are born in pairs or even triplets. This simple, staggering fact reframes our entire perspective. Our quiet, single-sun solar system might be the cosmic outlier, not the standard. So, what exactly is a binary star system, and how does such a dynamic arrangement actually work? At its heart, a binary system is a gravitational dance between two stars that are bound together, forever orbiting around a shared center of mass, a point in space known as the barycenter. Think of it like two people holding hands and spinning around. The point where their linked arms pivot is that central balance point. Depending on the star's masses, this barycenter can be located deep inside the more massive star or in the empty space between them. These stellar partnerships come in several distinct varieties, each with its own dramatic physics. In a close binary system, the two stars are locked in a tight, intimate embrace, whirling around each other in a matter of days or even hours. Their proximity leads to some of the most explosive phenomena in the cosmos. If one star evolves into a red giant, it can literally spill its own material onto its companion, a process called mass transfer. This can trigger colossal nova explosions or even set the stage for a supernova. On the other end of the spectrum are wide binaries, where the two stars are separated by vast distances, sometimes thousands of times the distance from the Earth to the Sun. Their orbital dance is a slow, graceful waltz that can take hundreds of thousands of years to complete a single circuit. In these systems, the stars live largely independent lives, their gravitational bond a faint tether across the interstellar void. And this is where the story gets truly fascinating for us, because planets can and do exist in these chaotic environments. The old belief was that the complex gravitational forces in a binary system would tear any forming planet apart or fling it into the depths of space. But we now know that's not true. Through advanced simulations and even direct observations of other star systems, astronomers have identified two primary ways a planet can achieve a stable orbit in a two-sun system. The first is called an S-type orbit, where a planet circles just one of the two stars, essentially treating its host star as the anchor and the other star as a distant, though influential, sun in its sky. The second type is a P-type or circumbinary orbit, where a planet orbits both stars together, tracing a wider, stable path around the entire binary pair. We've actually discovered real exoplanets in these configurations, worlds with two sunsets that were once only possible in the realm of science fiction. Understanding these orbital dynamics is absolutely crucial because it shatters the illusion that a binary system is inherently hostile to planets. It provides the fundamental astronomical proof that a world like Earth could, in theory, have formed and thrived even if our sun had a companion. So if binary systems are the cosmic rule and our sun is the exception, the question becomes almost unavoidable. Could our sun have had a companion star long ago? This isn't just idle speculation. It's a question that gave rise to one of the most provocative and chilling theories in modern astronomy, the Nemesis hypothesis. Proposed in the 1980s, this theory didn't just suggest our sun had a twin. It proposed that this twin was a bringer of death, a dark companion responsible for cyclical devastation on Earth. The catalyst for this idea was a startling pattern uncovered in the fossil record. Paleontologists examining the history of life on our planet noticed that mass extinction events, where a significant percentage of Earth species vanish, seemed to occur with a rough periodicity of about 26 million years. It was as if a cosmic clock was ticking, and with every chime, life was nearly reset. Scientists grappling with this grim timetable needed a mechanism, a celestial trigger that could operate on such a vast, regular timescale. The Nemesis hypothesis provided a terrifyingly elegant answer. It proposed that our sun is not alone, but is gravitationally bound to a distant, dim, and as yet unseen companion. This wouldn't be a brilliant twin like our sun, but a faint, failed star, a red dwarf, or even a brown dwarf, an object too small to ignite sustained nuclear fusion. This dark twin was given the name Nemesis after the Greek goddess of retribution. According to the model, Nemesis would follow a vastly elongated, elliptical orbit that takes it far out into the frozen reaches of our solar system, only swinging back in towards the sun every 26 million years. On its closest approach, its gravitational influence would act like a wrecking ball hurled into a cosmic construction site. It would violently perturb the Oort cloud, a vast spherical shell of icy planetesimals that surrounds our solar system far beyond the orbit of Pluto. This gravitational disruption would send a shower of long-period comets raining down into the inner solar system, a celestial hailstorm with Earth directly in the line of fire. The impact of just one of these massive icy bodies would be catastrophic, but a whole swarm of them would be an extinction-level event. The scenario is all too easy to visualize. A comet slams into the planet, blasting a continent-sized crater and hurling billions of tons of dust and vaporized rock into the upper atmosphere. Sunlight is blocked for months or even years. Photosynthesis grinds to a halt, global temperatures plummet in an impact winter, and the food chain collapses. This single, elegant mechanism seemed to explain the periodic dying of the light seen in the rocks. For a time, the hunt for Nemesis was a serious astronomical pursuit, with researchers scanning the skies for any faint, slow-moving object that could be our sun's deadly shadow. Yet, despite decades of increasingly sophisticated surveys, Nemesis has never been found. Modern sky mapping missions, designed to catalog every nearby celestial object down to a very faint magnitude, have found no evidence of a star or brown dwarf orbiting within the proposed distance. The astronomical community has largely moved on, concluding that while the periodicity of extinctions remains a fascinating puzzle, the Nemesis star is not the solution. The evidence for the pattern itself has also been questioned and refined, with some scientists arguing the timeline isn't as clockwork as it first appeared. So, if Nemesis isn't out there, does that mean the entire idea of a solar sibling is dead? Far from it. The failure to find a Death Star actually opens the door to a much more compelling and transformative possibility. What if our sun's companion wasn't a permanent, recurring specter of doom, but a temporary partner from the solar system's very earliest days? This shifts the narrative from a story of cyclical destruction to one of profound creation, suggesting that a twin star didn't periodically threaten Earth, but may have been essential in building it in the first place. The narrative, therefore, shifts dramatically from a dark, recurring specter of death to a brilliant, foundational partner in creation. This new theory proposes that our sun's original companion wasn't a faint, menacing dwarf, but a true twin, a star of comparable size and luminosity, born from the same swirling cloud of gas and dust. This was a stellar sibling, not a nemesis. In this revised picture of the solar system's infancy, the sky above a young Earth would have been illuminated by two blazing suns, a double dawn that painted the primordial landscape in a light we can now only imagine. The formation of such a system is not only possible but, given what we know about stellar nurseries, profoundly likely. Most stars are born in litters, and it's entirely plausible that our Sun and its twin coalesced at the same time, orbiting a mutual center of gravity in a relatively close embrace for the first few million years of their existence. But if this was the case, where did the twin go? The answer lies in the violent and chaotic environment of a young star cluster. Our solar system did not form in the quiet, empty space it inhabits today. It was born within a densely packed stellar nursery, surrounded by hundreds or even thousands of other newborn stars, all jostling for position in a gravitational free-for-all. In such a crowded neighborhood, close encounters were not just possible, they were inevitable. A passing star swinging too close to our nascent binary system could have acted as a gravitational thief. The intricate three-body gravitational dance between our Sun, its twin, and the interloper would have been incredibly complex and unstable. In many simulated scenarios, the most common outcome is that the passing star plucks one of the binary partners away, breaking the gravitational bond and sending the stolen star spiraling off into the galaxy to live out its life in solitude. Our Sun, in this scenario, was the one left behind, the solitary remainder of a broken partnership. The evidence for this dramatic stellar divorce isn't just locked in computer models, it might be written into the very architecture of our outer solar system. The most compelling clue comes from a puzzling feature far beyond the orbit of Neptune, in the realm of icy bodies known as the Kuiper belt. Astronomers have observed that the orbits of some of the most distant objects seem to be clustered together, as if shepherded by an unseen gravitational influence. While one proposed explanation has been a hypothetical Planet 9, another equally valid explanation is the early presence of a second sun. A stellar twin, even for a short period, would have exerted a massive gravitational pull on these distant icy bodies. Its sudden removal would have left a distinct imprint on their orbits, a fossilized gravitational signature frozen in time, a ghostly handprint left behind after the hand itself had vanished. This theory doesn't just solve the mystery of a missing sibling, it elegantly addresses some of the most persistent puzzles of our solar system's formation. For instance, the strange, tilted orbit of the hypothetical Planet 9, if it exists, becomes much easier to explain if it was influenced by a second star. Even the very existence of the Oort cloud, that vast spherical shell of comets, is more readily understood with a binary model. A single star has a hard time capturing and holding onto so much material so far out. But a binary system, with its more complex and far-reaching gravitational field, acts as a much more effective net, trapping a huge population of icy planetesimals that would have otherwise escaped. The companion star's departure would then have left this captured cloud behind, explaining the immense reservoir of comets that surrounds us today. So, while the Nemesis theory was a story of Chinese letter destruction, this newer, brighter twin theory is one of construction and legacy. It suggests that our Sun's lost partner wasn't a destroyer of worlds, but a key architect that helped build the very solar system we call home, a co-author of our cosmic story whose contribution ended when it was pulled away by the tides of galactic motion. So where do we even begin to search for the ghost of a star that vanished billions of years ago? We look for its fingerprints, for the subtle ways its gravity would have sculpted the solar system before it disappeared. And some of the most compelling evidence isn't found by looking up at the stars, but by studying the frozen frontier at the very edge of our own planetary neighborhood. Out beyond the orbit of Neptune lies the Kuiper belt, a vast disk of icy remnants left over from the solar system's formation. It's like a cosmic archaeological site, preserving the conditions of our earliest days. And within this disk, astronomers have found something deeply puzzling: a population of extreme objects with orbits that simply don't make sense according to the standard model of a lone sun. Take an object like Sedna, one of the most distant known bodies in our solar system. Sedna follows a wildly elongated path that takes it from a point relatively close to the Sun out to an incredible distance, a journey lasting thousands of years. But here's the real mystery: its orbit is detached. At its closest approach, it never gets near enough to the giant planets for their gravity to have pulled it into such an extreme path. It's as if it was yanked out there long ago and then left completely isolated, a cosmic castaway with no explanation for how it got stranded. Sedna isn't alone either. Several other so-called extreme trans-Neptunian objects have been discovered with similar, strangely clustered orbits. They all seem to share similar arguments of perihelion, meaning the orientation of their closest approach to the Sun is oddly grouped together. This clustering is statistically very unlikely to happen by chance in a calm, orderly solar system. It's a clear signal that some significant external force must have acted upon them in the distant past. This is where the missing twin theory provides an elegant and powerful explanation. Imagine the early solar system with two suns instead of one. The combined gravitational field of this binary pair would have been far more extensive and complex than our suns alone. It would have created a much larger sphere of influence, capable of capturing and flinging these icy bodies into highly eccentric orbits. As these objects interacted with the binary gravity, they could have been shepherded into their strange, detached paths. Then, when the second star was gravitationally stolen away by a passing interloper, its influence vanished almost instantly on a cosmic timescale. The orbits of these distant objects were frozen in place, effectively fossilized. What we see today in the clustered orbits of Sedna and its kin could be the direct, lasting imprint of that second sun's presence, a celestial photograph from the solar system's infancy, capturing the moment our sun's partner was there. This idea gains even more traction when we compare it to the alternative explanation that's often proposed for these strange orbits: the existence of a large, undiscovered planet, often dubbed Planet 9. This hypothetical world, several times the mass of Earth, could theoretically generate the gravitational shepherding effect needed to explain the orbital clustering. And while Planet 9 is a fascinating possibility, the binary star model offers a compelling and perhaps more natural solution. A planet massive enough to create these effects would itself be on a very eccentric and tilted orbit, which raises its own set of formation challenges. How did such a large planet form out there or get thrown out there without disrupting everything else? A second sun, however, is a fundamental part of the initial system. Its gravity is immense, easily capable of sculpting the entire outer disk in a way that a single planet would struggle to match. The binary model doesn't require us to invent a new, unseen planet with its own complicated history. It simply asks us to consider that our sun's most fundamental relationship, its very identity as a single star, might be the result of a long-ago cosmic event. The ghost in the orbital machinery isn't a planet but a star. Now let's journey even farther out to the most distant and mysterious frontier of our solar system, the Oort cloud. If the Kuiper belt feels remote, the Oort cloud is almost mythical in its scale and isolation. Imagine a vast spherical shell of trillions of icy objects surrounding our entire solar system, stretching from about 2,000 times the distance from the Sun to Neptune, all the way out to a mind-boggling 100,000 times that far. We're talking about a region so enormous that light itself takes a full year just to travel from one edge to the other. This isn't a flat disk like the Kuiper belt or the asteroid belt. It's a gigantic, diffuse bubble of frozen primordial material, a cosmic deep freeze preserving the untouched building blocks of our planetary system. Here's the fascinating puzzle. For a solitary star like our Sun, the very existence of such a massive spherical cloud is surprisingly difficult to explain. Think about how the planets formed from a flat, spinning disk. Most of the material that didn't get incorporated into planets should have remained in that same general plane. So how did so much of it end up in this immense spherical shell so far away? The prevailing theory suggests that the gravitational nudges from the giant planets, particularly Jupiter and Saturn, scattered icy planetesimals outwards. While that can explain some objects reaching far distances, it struggles to account for the sheer number of bodies in the Oort cloud, and especially for how they achieved a perfectly spherical distribution. A lone star's gravitational pull weakens dramatically with distance, making it surprisingly inefficient at capturing and holding onto such a vast spherical swarm. It's like trying to corral a cloud of gnats with a single, faint whisper. Most of them would just drift away. This is where the presence of an early binary companion offers an astonishingly elegant solution. A system with two stars has a much stronger and more extensive gravitational reach. The combined gravity of the twin suns would have created a far larger capture cross-section, acting like a much wider net trawling through the protoplanetary disk. Icy debris scattered by the giant planets would have been far more likely to be snagged by this enhanced gravitational field and thrown into the distant spherical shell that became the Oort cloud. Not only would this process have been more efficient, but the complex gravitational interactions between the two stars would have naturally randomized the inclinations of these captured objects, easily explaining the spherical shape that a single star struggles to produce. The binary model doesn't just account for the Oort cloud's existence, it naturally explains its immense mass and its perfect halo-like structure. This isn't just a theoretical improvement, it has profound implications for the history of life on Earth. The Oort cloud is the source of most long-period comets, those spectacular, unpredictable visitors that swing into the inner solar system on orbits lasting thousands or even millions of years. If our Sun had a twin that helped build a more massive Oort cloud, then that means our early solar system would have been stocked with a far greater reservoir of cometary material. In one sense, this could have been a boon for life. These icy bodies are thought to have been one of the primary delivery mechanisms for water and complex organic molecules to the young Earth. A more massive Oort cloud could mean our planet was seeded with even more of these essential ingredients, potentially accelerating the emergence of life. Yet, this same reservoir also represents a constant, lingering threat. Any gravitational disturbance, whether from a passing star or the galactic tide, can dislodge these icy planetesimals and send them on a collision course with the inner planets. The legacy of that lost twin star, therefore, is a double-edged sword. It may have helped furnish our world with the very water of life, while also leaving behind a frozen arsenal capable of triggering existential catastrophe. To truly grasp the potential impact of a second sun, we must first travel back in time to the solar system's chaotic infancy, a period that was anything but the serene, orderly clockwork we see today. This was a violent construction zone, a celestial battlefield where the planets themselves were still taking shape through relentless collisions. In these first several 100 million years, the inner solar system was a shooting gallery of planetesimals, rocky and icy fragments left over from the planet-forming process. The giant planets Jupiter and Saturn were not the stable anchors they are now. They were likely migrating, their immense gravity carving paths through the protoplanetary disk and flinging debris in all directions. This era culminated in a cataclysmic event known as the Late Heavy Bombardment, a period around 4 billion years ago when the Moon, Mercury, Venus, and Earth were subjected to an intense planet-wide pummeling by asteroids and comets. The evidence is written across the face of the Moon, whose ancient highlands are scarred with immense craters, a silent testament to this epoch of cosmic violence. Now layer the presence of a second sun onto this already turbulent scene. In a young binary system, the gravitational dance becomes infinitely more complex. Instead of a single, central point of gravity dictating the motions of every object, you have two stars orbiting each other, their combined gravitational field creating a dynamic and shifting landscape of gravitational hills and valleys. This environment is far less stable for the smaller bodies trying to find peaceful orbits. A planetesimal minding its own business could be easily destabilized by the periodic tugs from the second star, its orbit perturbed just enough to send it on a new, dangerous trajectory crossing the paths of the inner planets. The binary partner acts as a gigantic gravitational stirrer, constantly churning the pot of primordial debris and dramatically increasing the likelihood of catastrophic collisions. This offers a powerful and elegant explanation for the intensity of the late heavy bombardment. Perhaps the sheer number of impactors wasn't just a result of the giant planet's migration alone, but was significantly amplified by the presence of our Sun's twin. As the two stars waltzed around each other, their gravitational influence could have shaken loose a vast reservoir of material from the outer disk, funneling it inward in a great shower of rock and ice. This would have turned a period of heavy bombardment into an absolute deluge, a celestial storm of unimaginable ferocity that reshaped the surfaces of all the terrestrial worlds. For Earth, this would have been a time of both destruction and, paradoxically, creation. While these impacts would have been globally sterilizing, vaporizing oceans and shattering the young crust, they may also have delivered vast quantities of water and the complex organic molecules that are the essential building blocks of life. The very violence that threatened to eradicate life may have ultimately supplied the ingredients for it to begin. The implications for Earth's own biography are staggering. One of the most profound mysteries of our planet's early history is the origin of the Moon. The leading theory, the giant impact hypothesis, posits that a Mars-sized body, often called Theia, slammed into the primordial Earth, blasting a colossal amount of material into orbit that later coalesced into our lunar companion. But what could have put Theia on such a catastrophic collision course in a single star system? Such a precise and devastating encounter is a bit of a statistical oddity. In a binary system, however, the chaotic gravitational environment makes such giant impacts far more probable. The second star's influence could have gradually nudged Theia from a stable orbit, setting it on a slow, fateful spiral toward its rendezvous with Earth. In this light, the existence of our Moon, that beautiful, silvery companion that has guided tides and inspired wonder for all of human history, might not be the product of a random freak accident, but a direct and likely consequence of our solar system's binary beginnings. Our entire world, with its unique daily cycle and stable axial tilt so crucial for climate regulation, may owe its very character to the gravitational mischief of a sun that is no longer there. The scars of the late heavy bombardment are most starkly visible on our Moon, a world without weather or plate tectonics to erase the evidence. Look through a telescope at the lunar highlands, and you're staring back in time at a landscape utterly shattered by impact. Craters like the sprawling Clavius, over 200 kilometers across, or the deep, complex Schrödinger basin on the far side, testify to an era when space was filled with projectiles. But this wasn't just a lunar event. Earth, with its greater gravity, would have been an even bigger target. While erosion has erased the physical craters, geologists find traces of this ancient violence in some of the world's oldest rocks, in formations like the Barberton Greenstone Belt in South Africa, where evidence of immense asteroid strikes is preserved in layers over 3.5 billion years old. This period of intense planetary assault has always presented a puzzle. What could have stirred up the solar system so effectively, delivering such a sustained and devastating rain of rock and ice? The standard explanation points to a gravitational reshuffling of the giant planets. The theory goes that as Jupiter and Saturn migrated in the young solar system, their shifting gravity acted like a cosmic slingshot, destabilizing the asteroid belt and the primordial disk of debris, flinging a cascade of material inward. But while planetary migration is a powerful mechanism, the sheer scale and duration of the late heavy bombardment pushes the limits of what this model can comfortably explain on its own. It's like trying to account for a 100-year flood with the mechanics of a seasonal storm. something seems missing from the equation. This is where the binary sun theory injects a potent and dynamic new variable into the celestial calculus. Imagine the early solar system not as a placid disk around a single star, but as a more complex, three-dimensional arena dominated by two stars in a tight orbital dance. The gravitational field would have been far from static. As the twin stars swung around their common center of mass, their combined pull would have created shifting zones of stability and chaos throughout the disk. Objects in the outer reaches, particularly in the primordial Kuiper belt and the scattered disk, would have been subjected to periodic gravitational kicks from the companion star. This is a process known as orbital resonance, where a periodic tug, repeated at just the right interval, can gradually pump energy into an object's orbit, making it more and more elongated. Over time, these subtle, rhythmic perturbations could have transformed the orbits of countless icy planetesimals and asteroids, pushing them from safe, circular paths into highly elliptical ones that dove directly into the inner solar system. This provides a testable, physical mechanism that supercharges the late heavy bombardment. The companion star acts as a gravitational pump, systematically funneling material from the outer system toward the terrestrial planets. It's not just a single, one-off event like planetary migration, but a continuous process that lasts for as long as the binary pair remains stable. Every orbit of the twin star provides another opportunity to nudge another icy body onto a dangerous new trajectory. This could explain why the bombardment was so intense and prolonged. The reservoir of outer solar system material was being actively and efficiently depleted by this dynamic stellar duo. The resulting onslaught would have been a mixed blessing for a young world like Earth. On one hand, these impacts delivered unimaginable destruction, with single strikes capable of vaporizing nascent oceans and sterilizing the planet's surface. On the other hand, they were also likely the primary delivery system for the volatile compounds water, carbon dioxide, ammonia, and complex organic molecules that would eventually form our oceans and atmosphere and provide the raw ingredients for life itself. The very cataclysm that threatened to erase Earth's potential may have been the event that ultimately furnished it with the essentials for a living future. This binary perspective doesn't just add another layer to the story, it offers a more unified and elegant explanation for the solar system's early violence. It connects the architecture of the outer solar system with its strange, detached objects like Sedna directly to the pockmarked surfaces of the inner worlds. The same gravitational hand that sculpted the orbits of those distant ice dwarfs is the same hand that could have flung the impactors that carved the great lunar basins. It turns two separate mysteries, the odd outer orbits and the inner solar system bombardment, into two sides of the same cosmic coin, both pointing back to a formative event that reshaped our entire planetary neighborhood. The ghost of the second sun, therefore, is not just a theoretical curiosity. Its influence is potentially written in the craters of the moon and the very chemistry of our world, a silent partner in the dramatic and violent construction of the solar system we inhabit today. Looking up at our solar system today, you might see a model of near-perfect order. The planets trace out their elliptical paths around the sun in what appears to be a single, flat plane, a cosmic racetrack where everyone stays in their lane. But when astronomers peer closer, they discover this tidy image is an illusion. The reality is far more interesting. Each planet's orbit possesses its own unique personality, a slight tilt or a subtle stretch that defies the expectation of perfect alignment. Mercury's path, for instance, is noticeably more elongated than the others, while the majestic ringed planet Saturn orbits with a tilt of over 2 degrees relative to Earth's own orbital plane. These minor deviations, these idiosyncrasies in the celestial dance, are more than just random noise. They could be the faint, lingering echoes of a much more dramatic and chaotic youth, a time when a second gravitational powerhouse was stirring the pot. In a pristine, single-star formation model, where a lone sun condenses from a smoothly collapsing cloud, the natural outcome is a system of remarkable flatness. Conservation of angular momentum dictates that the spinning cloud flattens into a disk, much like a ball of pizza dough spins into a flat crust. Within this disk, planets coalesce, inheriting that same general direction of motion. We would therefore expect the final planetary orbits to be almost perfectly coplanar, with negligible inclinations and near-circular paths. The fact that our solar system mostly fits this description is why the nebula hypothesis has been so successful. Yet, those persistent small deviations are the tantalizing clues that the full story might be more complex. They are the wrinkles in an otherwise smooth narrative, hints that the protoplanetary disk may have experienced some external turbulence during its formative years. This is where the gravitational influence of a second star provides a compelling explanation. Imagine the young solar system as a whirlpool of gas and dust, but with two brilliant centers of gravity orbiting each other at its heart. This binary configuration would not create a serene, stable disk. Instead, the gravitational pull from the companion star would act as a continuous source of perturbation. As the twin suns waltzed around their common center of mass, their combined gravitational field would create ripples and resonances throughout the protoplanetary material. These are not violent, disruptive shocks, but rather persistent, rhythmic tugs that can gradually warp the entire disk over millions of years. Planetesimals and growing planetary embryos would find their orbits gently nudged, their inclinations slowly pumped up, like a child on a swing receiving a steady push at just the right moment to go higher and higher. The planets we see today, with their slight orbital tilts, could therefore be the fossilized results of this ancient gravitational stirring. The process wouldn't have affected all planets equally, which is precisely what we observe. A world forming closer to the binary pair, deep within their potent gravitational well, might have been more resistant to inclination changes. Meanwhile, a planet forming farther out, where the disk was thinner and the periodic tug from the second star was more pronounced, could have been more easily knocked into a slightly tilted orbit. This offers a natural mechanism to explain the varied orbital planes without invoking random chance or extraordinarily rare events. The gravitational hand of the lost twin, gently warping the disk over eons, left behind a permanent signature in the paths of the worlds it helped shape. Consider the case of the dwarf planet Pluto, which famously orbits in a plane tilted a staggering 17 degrees from the ecliptic. While Pluto is now considered a Kuiper belt object, its extreme orbit has always been a puzzle. In the standard model, it's difficult to explain how such a large body acquired such a pronounced inclination. But in a young binary system, Pluto's path becomes far less anomalous. The persistent gravitational nudges from the second star could have easily lifted Pluto and many of its icy cousins into their highly inclined orbits. This same process would have also affected the larger planets during their final stages of growth. The slight but measurable inclinations of Jupiter, Saturn, and the others may not be accidents of formation, but rather the expected outcome of growing up in a dynamic two-sun environment. The current architecture of our solar system, in all its beautiful imperfection, may be the most enduring testament we have to a brilliant partner our sun lost long ago. So, we've explored how a second sun could explain the strange orbits at the edge of our solar system and the intense bombardment that scarred our young planets. But there's another compelling piece to this cosmic puzzle, one that becomes apparent only when we look beyond our own celestial neighborhood and survey the wider galactic landscape. When astronomers began discovering planets around other stars, they expected to find solar systems that looked roughly like our own, but the universe had a surprise in store. One of the most common types of planets we've found in the Milky Way is something our own system completely lacks: a world known as a super-Earth. These are planets with masses larger than Earth's but smaller than Neptune's, typically ranging from about 2 to 10 times the mass of our home world. They are the galactic standard, appearing in vast numbers around other stars, and yet in our own solar system, that specific category is conspicuously entirely empty. It's a glaring anomaly, a quiet gap in our planetary lineup that begs for an explanation. If these planets are so common everywhere else, why don't we have one? This missing super-Earth presents a genuine mystery for the standard model of our solar system's formation. In that model, the protoplanetary disk around our young sun had a specific amount of material and a particular distribution of elements. Within that context, it's possible that the conditions simply didn't arise to form a planet in that specific size range between the orbits of Mars and Jupiter. Perhaps the material in that region was too scattered, or the gravitational influence of Jupiter ultimately prevented a larger world from coalescing. But when you step back and see just how ubiquitous these planets are elsewhere, this explanation starts to feel a bit like a cop-out. It's as if you surveyed every house on a street and found that 90% of them had a specific type of room, a sunroom, let's say, but your own house, built from the same basic blueprint in the same neighborhood, completely lacks one. You'd naturally wonder if something unique happened during its construction. This is where the idea of an early binary companion offers a dramatic and elegant solution. The presence of a second star doesn't just add a new factor. It fundamentally transforms the entire gravitational environment in a way that could have actively prevented a super-Earth from forming, or, even more strikingly, could have violently evicted one that did. Let's consider the first possibility, that a binary partner prevented a super-Earth from ever forming in the first place. In a single star system, the protoplanetary disk is a relatively calm, if busy, construction site. Planetesimals collide and stick together, gradually building up into planetary embryos and eventually full-fledged planets over millions of years. But introduce a second star and the dynamics become far more chaotic. The gravitational pull from the companion star creates what scientists call gravitational resonances, specific orbital distances where the periodic tugs from the second star align with a budding planet's orbit. These resonances act like powerful vibrational nodes. Imagine trying to build a delicate sandcastle while someone nearby is rhythmically stomping on the ground. The constant, rhythmic shaking would prevent the sand grains from settling into a stable structure. In the same way, these gravitational resonances could have stirred up the planet-forming material in the region where a super-Earth would typically coalesce, keeping the dust and planetesimals too agitated to accrete into a larger world. The material remains scattered, never managing to clump together into a single, substantial planet, thus leaving that orbital zone empty. The second, and perhaps even more compelling, scenario is that a super-Earth did indeed begin to form, only to be brutally ejected from the solar system in its infancy. This is not as far-fetched as it might sound. Our current models of planetary formation suggest that the early solar system likely had more planets than it does today. It was a crowded and violent place where gravitational shoving matches were common. In a single star system, these interactions can lead to planets being flung into the sun or out into interstellar space, but it's often a complex process. Now add the immense and dynamic gravity of a second sun into the mix. The binary system becomes a highly efficient ejection machine. The complex three-body or even four-body gravitational interactions between the two stars and the developing planets would have been incredibly unstable. A young super-Earth forming in the inner solar system could have had its orbit dramatically perturbed. A close gravitational encounter with Jupiter, amplified by a well-timed pull from the second star, could have provided the precise kick needed to send the fledgling world careening out of the solar system entirely, condemning it to an eternal journey through the cold, dark interstellar void as a rogue planet. This idea of planetary ejection helps explain another curious feature of our solar system, its apparent calm and order. We have 4 terrestrial planets in stable, nearly circular orbits with a vast gap, the asteroid belt, separating them from the gas giants. This clean division is not necessarily a given. In other systems with super-Earths, we often see these larger rocky planets orbiting much closer to their stars, sometimes in compact packs, suggesting a very different formation history and migratory path. The violent ejection of a major planetary body would have been a cataclysmic event for the young solar system, but it could have also been a profoundly organizing one. The gravitational upheaval required to expel a super-Earth would have acted like a cosmic reset button, clearing out leftover debris and dynamically heating the orbits of the remaining planets. This turbulence would have been followed by a period of settling as the planets found new, stable orbits in the aftermath of the chaos. The departure of the second star would have then frozen this new, more orderly configuration in place. In this light, the quiet, predictable solar system we know today might be the direct result of an ancient titanic conflict, a gravitational drama that saw both a stellar twin and a planetary sibling lost to the galaxy. Our system's unusual lack of a super-Earth, therefore, might not be a quirk of formation, but a scar from a traumatic childhood, a silent testament to the violent gravitational forces that once sculpted our cosmic home. To truly understand the fate of our Sun's potential twin, we must expand our view beyond the familiar planets and comets of our own system and look at the Sun's place in the galaxy itself. Our Sun was not born in the quiet isolation it enjoys today. It began its life within a bustling stellar nursery, a vast, dense cloud of gas and dust where thousands of stars were igniting all at once. In such a crowded and dynamic environment, newborn stars are initially gravitationally bound to one another, forming what astronomers call an open cluster. For the first few tens of millions of years, these sibling stars would have orbited a common center, their brilliant light collectively illuminating the nebula from which they formed. It was within this vibrant celestial city that our Sun and any potential twin spent their earliest years. But stellar cities don't last forever. The gravitational bonds within an open cluster are relatively weak, and over time, the relentless tidal forces of the Milky Way's rotation, along with close gravitational encounters between the stars themselves, begin to pull the cluster apart. Stars are gradually stripped away, drifting apart like dandelion seeds on a cosmic breeze. Within a few 100 million years, the cluster dissipates entirely, and its once close stellar siblings are scattered across the vast expanse of the galactic disk, destined to orbit the galaxy's center on their own independent path. This is the inevitable fate of all open clusters, and it is almost certainly what happened to the Sun's birth cluster. The sibling stars that once shared our cosmic cradle are now lost, their light diluted among the hundreds of billions of other stars in the Milky Way. So, if the Sun's entire family has been scattered to the winds, how could we ever hope to find them, let alone identify a specific twin? This is where modern astronomy turns to the power of forensic stellar chemistry. The key insight is that all stars born from the same molecular cloud share a unique chemical signature, a kind of cosmic DNA. When a star forms, it condenses from a specific parcel of interstellar gas that has its own distinct mix of elements, forged in the hearts of long-dead generations of stars. This mix includes not just common elements like hydrogen and helium, but also specific ratios of heavier elements, the astronomical equivalent of trace minerals. Two stars born from the same cloud will have nearly identical proportions of elements like iron, silicon, and oxygen. More importantly, they will share the same distinct pattern of rare, oddball elements, things like yttrium, europium, and even specific isotopes of more common materials. Finding these long-lost siblings, therefore, becomes a monumental task of chemical fingerprinting. Astronomers are undertaking this challenge through massive, ambitious galactic archaeology projects, most notably the European Space Agency's Gaia mission. Gaia is not just mapping the positions and motions of over 1 billion stars, it is also precisely measuring their chemical compositions. The goal is to find stars that are not just moving through space on a similar path to our Sun, a clue that they might have originated in the same region, but that also share our sun's exact chemical makeup. It's like trying to find a specific needle in a galaxy-sized haystack by identifying all the other needles that were forged in the same factory. Researchers have already identified a number of promising candidate siblings this way, stars that share our sun's unique chemical recipe and whose orbital paths can be traced backward in time to intersect with the sun's own path billions of years ago. This brings us directly back to our core mystery. Could one of these rediscovered stellar siblings actually be the very twin we've been searching for all along? The distinction here is crucial. A stellar sibling is any star born from the same cloud, while a stellar twin would have been our sun's specific binary partner, the other half of that intimate gravitational dance. The stars we are finding through chemical fingerprinting are siblings, but they were not necessarily the sun's immediate binary companion. They were more like cousins who lived in the same stellar neighborhood. However, finding these siblings dramatically increases the likelihood that our sun did, in fact, have a true twin. If we can confirm that the sun was born in a cluster with hundreds or thousands of other stars, and we know that most stars in such environments form in binary or multiple systems, then the statistical probability that our sun was once part of a binary pair becomes overwhelmingly high. The discovery of any solar sibling is a powerful piece of circumstantial evidence supporting the entire binary theory. The most thrilling possibility is that the sun's specific binary twin is still out there, waiting to be identified among the growing list of chemical matches. It would be a star of very similar mass and composition to our sun, a true fraternal twin. Its current motion would be the biggest clue. While most of the sun's siblings have drifted randomly across the galaxy, a star that was once gravitationally bound to the sun would have been flung away on a very specific trajectory during the event that broke the binary bond, whether it was a close stellar encounter or the cluster's general dissolution. By modeling these chaotic gravitational interactions, astronomers can predict the kinds of orbits that an escaped twin might now follow. Finding a star that not only matches the sun's chemistry but is also on such a predicted path would be the ultimate smoking gun. It would transform the binary sun theory from a compelling idea based on orbital oddities in our own solar system into a confirmed chapter of our cosmic history, directly linking the ghost of a second sun in our past to a real, shining star in our present-day sky. But to understand how such a profound separation could occur, we need to zoom out from our solar system and see it not as a static island, but as a tiny ship sailing through the vast, dynamic ocean of the Milky Way galaxy. Our sun, along with every other star, is in constant motion, orbiting the galactic center once every 230 million years or so. This isn't a serene cruise, it's a journey through a cosmos filled with invisible forces and gravitational obstacles that constantly tug and pull at everything within it. For a wide binary star system, the kind our sun might have been part of this galactic environment is not a peaceful backdrop. It is an active, relentless agent of change, capable of slowly and patiently prying two stars apart over the eons. The primary forces at work here are the subtle but immense pull of the galaxy's overall gravity, the occasional close brush with a passing star, and the gravitational shadows cast by giant molecular clouds, the very birthplaces of new suns. Let's start with the most pervasive force, galactic tides. You're familiar with how the moon's gravity creates tides on Earth, pulling the oceans into slight bulges. The Milky Way exerts a similar, though vastly more complex, tidal force on every star within it. Because the galaxy's mass is not evenly distributed, it's concentrated in the central bulge and the sprawling disk. The gravitational pull on a star varies depending on its position. For a wide binary system, this creates a constant, gentle stress. Imagine two boats tied together with a long rope sailing across a wide bay. If the water on one side of the boats is slightly deeper, it will pull that boat a little faster, creating tension on the rope. Galactic tides work in a similar way, exerting a differential pull on the two stars in a binary pair. The star momentarily closer to the galactic center feels a slightly stronger tug than its partner, and over billions of years, this recurring, rhythmic stress pumps energy into the binary system, very gradually stretching its orbit and making it wider and more fragile. This process is dramatically accelerated when our solar system passes through one of the galaxy's giant molecular clouds. These are not wispy cirrus clouds, but colossal, dark structures containing enough gas and dust to form millions of stars. They are the cosmic mountains and continents of the interstellar medium. When a star system like ours plows into one of these behemoths, the gravitational landscape shifts violently. The cloud's immense mass creates a powerful, localized gravitational field that can violently perturb the delicate orbital dance of a wide binary. Sophisticated computer simulations vividly show what happens next. As the binary system passes through the cloud, the two stars experience sudden, sharp gravitational kicks from the cloud's densest clumps. These kicks can be enough to radically alter the binary's orbit, either tightening it dramatically or, more often, giving one star just enough extra velocity to overcome their mutual gravitational bond. The once stable partnership is shattered, and the two stars are sent flying apart on independent paths around the galaxy, their connections severed forever. On top of these large-scale forces, there are the random, close encounters with other stars. Even in the vast spaces between stars, the sheer number of suns means that close passes are inevitable over billions of years. A solitary star wandering too close to a wide binary system engages in a brief but intense gravitational tug-of-war. The mathematics of this three-body interaction are famously chaotic. The slightest difference in the incoming star's trajectory can lead to wildly different outcomes. In many simulated scenarios, the most common result is that the interloper star steals one of the binary partners, breaking the original pair and forming a new, temporary binary with the stolen star before that too is likely broken up by a future encounter. The original partner left behind, in this case our Sun, becomes a solitary star, a cosmic widow carrying only the gravitational echoes of its lost companion. The dissolution of a wide binary, therefore, isn't a rare or catastrophic failure. It's the statistically expected fate for most such systems given enough time and enough journeys around the galaxy. When we integrate all of these forces, the persistent tug of galactic tides, the shocking gravitational punches from giant molecular clouds, and the random stellar interloper, a clear and compelling narrative emerges. The breaking of our Sun's binary bond becomes not a mysterious catastrophe, but a natural and even predictable phase in the life of a star born within the busy disk of a spiral galaxy. The binary system's fate was essentially sealed from the moment it formed. If the companion star was in a wide orbit, the gravitational glue binding it to our Sun was relatively weak, making it exceptionally vulnerable to these external forces. Over the first few 100 million years, as the Sun's birth cluster dissipated, these galactic influences would have worked in concert, gradually loosening the twins' grip until a final, decisive encounter provided the last nudge needed for a permanent separation. This cosmic drift explains why we don't see the companion today. It wasn't flung into some specific, predictable orbit we can easily pinpoint. Instead, it was gently, or perhaps not so gently, set adrift on the galactic currents, its location now lost among the hundreds of billions of other stars in the Milky Way, a silent testament to the dynamic and ever-changing nature of our galactic home. The very essence of a star, the specific blend of elements that fuels its fire and builds its planets, acts as an unchangeable birth certificate, a chemical fingerprint locked in place at the moment of its creation. To uncover the truth about our Sun's possible twin, we turn from the grand scale of orbital mechanics to the infinitesimally small world of atomic physics, using a technique that feels almost like magic, stellar spectroscopy. This is the art and science of reading starlight itself, and it allows us to perform what is essentially a cosmic DNA, a test on any star in the galaxy. When a star forms from a collapsing cloud of interstellar gas and dust, it inherits the unique chemical signature of that particular cloud. This signature isn't just about having more or less iron or oxygen. It's about the precise ratios between dozens of different elements, a pattern so specific that it's highly unlikely to be exactly duplicated in another region of the galaxy. Think of it like this: two families might both have flour, sugar, and eggs in their pantry, but only one family will have that exact, unique combination of a specific brand of vanilla, a particular type of sea salt, and a trace of saffron that gives their recipes a distinctive flavor. Stars from the same stellar nursery share that same cosmic pantry, and that distinctive flavor is written in their light. So how do we read this celestial recipe? The process begins when we point a powerful telescope, equipped with a specialized instrument called a spectrograph, at a star. The star's light, which seems like a pure, white beam to our eyes, is actually a rainbow containing every color of the visible spectrum. The spectrograph acts like a cosmic prism, splitting that light into its full, vibrant spectrum. But this isn't a smooth, perfect rainbow. Superimposed on it are countless dark lines, like a complex barcode etched across the colors. These lines are the key. They are called absorption lines, and each one is created when a specific chemical element in the star's outer atmosphere absorbs a very specific wavelength or color of light. Every element has its own unique set of lines. Hydrogen has one pattern, iron has another, calcium yet another. By carefully mapping the pattern and depth of these dark lines, astronomers can determine not only which elements are present in the star, but also their exact abundances. This spectrum becomes a unique identifier, a chemical passport for that star. To find our sun's long-lost family, astronomers aren't just looking for stars that are broadly similar in composition. They are engaged in a painstaking process of chemical tagging, searching for stars whose spectra are a near-perfect match to our sun's across a wide range of elements. This goes far beyond the major building blocks. The most telling clues often come from the subtle traces of rare elements like europium, yttrium, and barium, and even the specific isotopes of more common ones. The probability of two unrelated stars having the exact same abundances of all these different materials is astronomically low. So, when we find one that does, it's a powerful indication that they were forged in the same cosmic crucible. The most ambitious project in this search is the European Space Agency's Gaia mission, which is not only mapping the positions and motions of over 1 billion stars, but also providing detailed spectroscopic data for millions of them. This vast treasure trove of information is allowing scientists to sift through the galactic population and identify those rare stars that share our sun's specific chemical fingerprint. This brings us to the tangible evidence right here in our own solar system, locked within the most ancient rocks we can find. We don't need to look to distant stars alone to find our sun's birth signature. We carry it with us. Meteorites, particularly a primitive class known as carbonaceous chondrites, are time capsules from the very dawn of the solar system. They are remnants of the original protoplanetary disk that never formed into a planet, and as such, they preserve the chemical composition of that primordial cloud in pristine condition. When we analyze the elemental abundances in these ancient space rocks, they match the spectroscopic signature of our sun with remarkable fidelity. This confirms that the sun's spectrum is a true reflection of the material from which it formed. Therefore, any star out there that matches the sun's spectrum also matches the composition of our solar system's building blocks. It is a direct sibling born from the same reservoir of gas and dust. Now, imagine that among the growing list of solar siblings identified by Gaia and other surveys, we find one that is not just a chemical match, but also a match in mass and age to our sun. This would be the holy grail, the prime candidate for being the lost twin. While a general sibling could be any star from the same birth cluster, A true twin would be one of nearly identical mass, as binary partners often form together from a single fragmenting core within the larger cloud. Finding a star that is both a chemical and a physical twin would provide the most compelling evidence yet that our Sun was once part of a binary pair. Its current motion through the galaxy would then become the final piece of the puzzle. By running gravitational simulations backwards in time, astronomers could test if its path is consistent with having been gravitationally unbound from our Sun during the dissolution of their birth cluster. The convergence of chemical, physical, and dynamical evidence would build an overwhelming case, turning a captivating theory into a well-supported chapter of our cosmic autobiography, written in the elemental language of the stars themselves. This brings us to one of the most profound and personal questions at the heart of this entire cosmic mystery. Could we even be here to ponder it? If Earth once basked under two suns, what does that mean for the very possibility of life? The anthropic principle offers a fascinating lens through which to view this question. In its simplest form, it observes that the universe we observe must be compatible with the existence of observers. We find ourselves on a planet with just the right conditions for life, so we naturally look back and assume those conditions were inevitable, but were they? The idea of a binary system forces us to confront the possibility that our planet's serene, life-friendly environment wasn't a foregone conclusion, but the result of a very specific and perhaps precarious series of events. At first glance, a second sun seems like a recipe for planetary chaos, presenting a host of formidable challenges to habitability. The most obvious concern is the potential for extreme and unpredictable temperature swings. In a binary system, a planet's climate isn't governed by the steady, reliable rhythm of a single star. Instead, it experiences the complex interplay of two light sources. Depending on the orbital configuration, a world could face periods of intense double-star heating followed by stretches of relative coolness when the stars are on opposite sides of its orbit. This could lead to wild climatic oscillations, with liquid water freezing and boiling in dramatic cycles, creating an environment far too volatile for the delicate chemistry of life to ever gain a stable foothold. Furthermore, the gravitational tug-of-war between two stars could potentially destabilize a planet's own orbit, either slowly pushing it out into the frigid outer darkness or pulling it in toward a scorching stellar embrace. From this perspective, a binary system appears to be a hostile, unpredictable place, a cosmic roller coaster where the gentle, stable conditions we enjoy on Earth would be nearly impossible to maintain. Yet, this intimidating picture is only one side of the story. When we shift our perspective, the presence of a second sun transforms from a potential obstacle into a possible cosmic facilitator. Consider the early Earth, newly formed and still cooling. The young sun was significantly dimmer than it is today, emitting only about 70% of its current energy. This creates what scientists call the faint young sun paradox. According to our models, Earth should have been a frozen, global snowball for its first 2 billion years, and yet the geological record clearly shows evidence of liquid water and even early life. Something was keeping the planet warm, while a thicker early atmosphere rich in greenhouse gases like methane and carbon dioxide is the leading explanation. A stellar companion offers another compelling solution. A second sun, even a smaller, cooler one, would have provided a crucial supplemental heat source. Its additional energy could have raised the baseline temperature of the entire inner solar system, effectively pushing the habitable zone outward and ensuring that Earth remained consistently warm enough for liquid water to persist on its surface. In this scenario, the twin suns didn't threaten life. They acted as a dual-engine heating system, preventing a global deep freeze and creating the stable, temperate cradle that life needed to emerge. The type of stellar companion matters immensely here. The binary model that best supports this life-friendly scenario is not the tight, chaotic embrace of a close binary, but the more stately and predictable dance of a wide binary. If the second star was a smaller, stable red dwarf orbiting at a considerable distance, its influence would have been profound yet gentle. It would have provided a constant, warm glow in the sky, a second, perpetual sunset or sunrise without the violent gravitational disruptions of a closer partner. This steady, additional illumination could have significantly accelerated the pace of planetary evolution. With more consistent warmth, the chemical reactions that led to the first self-replicating molecules might have occurred more readily. The extended daylight hours or the perpetual twilight of a double-sun sky could have provided more energy for early photosynthetic organisms, potentially speeding up the oxygenation of the atmosphere. The very length of days, seasons, and years would have been different, governed by the complex orbital periods of two stars, creating a unique environmental rhythm that might have been just as conducive to life's origins as our own single sun cycle, if not more so. Ultimately, the anthropic principle reminds us that we are the products of our environment. We exist because the conditions on Earth were right, and we naturally assume that our single sun system was the only way to achieve that. But the universe is a place of immense variety and possibility. The discovery of exoplanets in binary systems has already shattered the illusion that such environments are sterile. Our own solar system's peculiarities, from the moon's origin to the strange outer orbits, point toward a more dynamic past. Perhaps the question isn't whether a binary system could support life, but whether our specific brand of life is the direct result of one. The presence of a second sun in our past could have been the crucial, extra ingredient that tipped the scales, providing just enough warmth, just enough stability, or just the right gravitational nudge to set Earth on its unique course toward becoming a living world. The ghost of that lost twin, therefore, might not be a specter of destruction, but a silent, foundational partner in the greatest story ever told, the story of how a swirling cloud of stardust eventually learned to look back up at the sky and wonder about its own origins. And while the scientific evidence for a second sun is compelling, the story doesn't end with computer simulations and orbital mechanics. To find another layer of this mystery, we must turn from the telescopes of modern observatories to the ancient texts and oral traditions of humanity itself. Scattered across the globe in the foundational myths of countless cultures, there are strange and persistent stories that speak of a time when the sky was different, when a second light once shared the heavens with our own familiar sun. These aren't scientific records, of course, but they may be something equally powerful: cultural memories passed down through generations and encoded in allegory and symbol, perhaps preserving the echo of a real, world-altering astronomical event from our deep past. In Chinese mythology, one of the most famous tales is that of the 10 suns. The legend tells of a time in the distant past when not one, but 10 suns would traverse the sky, each taking its turn on a 10-day cycle. They were the children of the supreme god Dai Jun and the sun goddess Zi, and they lived in a massive mulberry tree at the edge of the world. The story goes that one day, the 10 suns grew bored of their orderly routine and decided to appear in the sky all at once. Their combined heat scorched the earth, boiling the rivers and withering all plant life, threatening to eradicate humanity. In response, the great archer Hui was summoned. With his divine bow, he shot down 9 of the 10 suns, leaving only the one we see today to provide a gentle and life-sustaining light. On the surface, this is a classic myth explaining the nature of the sun. But could it also be a poetic retelling of a more specific event? Perhaps the 9 suns were a mythological interpretation of a brilliant second star whose eventual disappearance from the sky, whether through a stellar encounter or simply drifting away, was remembered as being shot down by a celestial archer, a hero who saved the world from a burning, double-starred sky. Journeying to the other side of the world, we find strikingly similar themes in the Americas. Among the indigenous peoples of the Andes, there are traditions that speak of a time before the Incas when the world was plunged into a period of prolonged darkness after a great cataclysm. Following this extended night, the legend says 2 suns appeared in the sky. This period of dual illumination was said to be one of immense heat and difficulty. While these stories are often tied to cultural understandings of creation and destruction cycles, the recurring motif of a second sun is difficult to ignore. It appears as a disruptive force, an anomaly in the natural order that required a cosmic correction. In ancient Egypt, the sun god Ra was sometimes depicted in multiple forms, representing his journey across the sky. But some interpretations of certain texts hint at a more adversarial relationship with another celestial light, perhaps a symbolic struggle between a dominant and a lesser sun. These myths, separated by vast oceans and entirely unconnected cultures, share a common thread, a memory of a sky that was once fundamentally different and more dangerous. The human brain is a pattern-seeking engine, and our ancestors were unparalleled astronomers, meticulously tracking the movements of celestial bodies. A sudden, dramatic change in their sky, the appearance, or more likely, the gradual and then final disappearance of a second bright object, would have been an event of such profound significance that it would be woven into the very fabric of their cultural identity. It would become a foundational story told and retold around campfires for thousands of years, its details shifting and transforming with each generation, but its core intact. Once, long ago, there was another light in the sky. Skeptics rightly point out that these stories can be explained in other ways. The second sun could be a metaphorical representation of a particularly bright comet, a supernova, or even a massive volcanic eruption that filled the atmosphere with ash, creating the optical illusion of multiple suns through halos and sundogs. These are all valid interpretations, yet the sheer consistency of the theme is what gives pause. When disparate cultures from Asia to South America all preserve stories about a time of multiple suns and a subsequent celestial battle or correction that restored the single sun we know today, it invites us to consider a more unified global cause. A cometary explosion might be remembered by one culture, but would it create the same specific motif of a second, stable sun across so many others? The mythological record does not prove the binary sun theory, but it adds a profound and deeply human dimension to the scientific investigation. It suggests that the ghost of a second sun may live on not only in the strange orbits of distant ice dwarfs, but also in the oldest stories we have ever told, a faint but persistent whisper in our collective memory of a time when our world was lit by a different kind of light. This journey into the possibility of Earth's twin suns inevitably leads us into more speculative territory, where scientific hypothesis and ancient mystery sometimes collide in fascinating ways. One of the most famous and controversial examples of this is the story of the Dogon people of Mali and their purported knowledge of the star system Sirius. For centuries, the Dogon have held cosmological traditions that describe Sirius, the brightest star in our sky, as having a tiny, incredibly dense and invisible companion. They call this companion star Potolo, and their legend state it orbits Sirius every 50 years and is made of a metal heavier than iron, a substance so heavy that all earthly beings combined cannot lift it. To modern astronomy, this description is stunningly accurate. Sirius does indeed have a companion, Sirius B, which is a white dwarf, a stellar remnant so dense that a single teaspoon of its material would weigh many tons. The orbital period is almost exactly 50 years. The apparent precision of this ancient knowledge, recorded long before telescopes could ever hope to see the faint Sirius B, has fueled decades of debate and speculation. How did the Dogon come by this information? One popularized explanation, championed by authors like Robert Temple in his book, The Sirius Mystery, is that this knowledge was given to them by visitors from the Sirius system itself, ancient astronauts who imparted advanced astronomical wisdom. This idea was eagerly adopted by the ancient astronaut theory, which posits that extraterrestrial beings visited Earth in the distant past and guided human development. In this narrative, the Dogon traditions become proof of that contact, and by extension, the prevalence of binary star systems in the galaxy is used to suggest that our own solar system's potential binary past might also be the result of, or connected to, such extraterrestrial intervention. It's a captivating story that ties the cosmic ordinary binary stars to the extraordinary idea of alien teachers. However, when we subject the Dogon mystery to rigorous scientific and historical scrutiny, a more complex terrestrial picture emerges. Anthropologists and astronomers who have reinvestigated the claims point out that the Dogon were in contact with Western missionaries and explorers for decades before the ethnographers who recorded the Sirius stories arrived in the 1930s and 40s. It is entirely possible that this astronomical knowledge, which was becoming established in the West in the early 20th century, was transmitted to the Dogon and then integrated into their existing mythological framework, a process known as cultural assimilation. Furthermore, critical analysis of the original field notes suggests the Dogon descriptions were not as precise as later popular accounts claimed, and their cosmological system is deeply symbolic, not necessarily a literal star chart. The white dwarf's immense density, for instance, is a concept that fits neatly into both modern physics and ancient symbolic traditions about spiritual weight and significance. This isn't to dismiss the richness of Dogon cosmology, but rather to highlight how a cultural tradition can be reinterpreted through a modern, speculative lens. This distinction is crucial for our exploration. The scientific hypothesis that our Sun may have had a binary companion is built on a foundation of orbital mechanics, gravitational physics, and forensic chemistry. It makes testable predictions about the structure of the Kuiper belt, the formation of the Oort cloud, and the chemical fingerprints of stellar siblings. It is a model that can be, and is being, challenged and refined through observation and simulation. In stark contrast, the ancient astronaut interpretation of the same idea is not scientifically testable. It resides in the realm of belief and interpretation, often relying on selective evidence such as the Dogon stories, while ignoring more conventional explanations. Conflating these two very different approaches does a disservice to both. It robs the scientific inquiry of its rigor and oversimplifies the profound cultural and spiritual value of ancient myths by reducing them to potential alien instruction manuals. The enduring appeal of these speculative ideas, however, reveals something fundamental about us. The human mind craves narrative and meaning. The notion that our planet's history was shaped by a dramatic celestial event, whether the departure of a twin star or the arrival of star-faring teachers, satisfies a deep-seated desire for a grand, purposeful cosmic story. The scientific model of a binary past provides a different kind of story, one of dynamic chaos and gravitational chance, where our existence is the product of immense, impersonal forces. Both narratives attempt to answer the same profound question: where do we come from? One looks for answers in the stars themselves through the patient accumulation of data, while the other looks for answers from behind the stars in the possibility of intelligent design or intervention. Recognizing this distinction allows us to appreciate the scientific theory for its explanatory power, while still understanding the human yearning that fuels the more speculative interpretations. The true mystery may not be whether ancient aliens told us about binary stars, but why we are so compelled to look to the heavens for our origin story, searching for twins, teachers, or any sign that we are not alone in the vast and silent cosmos. So we arrive at the present day, armed with supercomputers, space telescopes, and a profound new question to ask the cosmos. The ghost of a second sun is no longer just a theoretical specter. It has become a tangible target in a modern astronomical treasure hunt. The quest has shifted from asking "what if" to actively searching for "where is it?" And the tools we now have at our disposal are nothing short of revolutionary. This isn't about scanning the skies with hopeful glances anymore. It's about conducting a systematic, galactic-scale investigation, sifting through the light of 1 billion stars to find the one that shares our sun's unique origin story. The key to this search lies in two fundamental pieces of evidence: a shared motion through the galaxy and an identical chemical fingerprint. Finding a star that matches on both counts would be as close to a smoking gun as we can get, and the mission making this possible is the European Space Agency's Gaia Space Observatory. Think of Gaia as the ultimate cartographer of the Milky Way. Since its launch in 2013, this remarkable spacecraft has been engaged in a monumental task, creating the most precise three-dimensional map of our galaxy ever assembled. It's not just plotting where stars are, it's tracking where they are going. Gaia measures the positions, distances, and motions of over 1 billion stars with astounding accuracy, pinning down their subtle movements across the sky with a precision equivalent to measuring the diameter of a human hair from 1,000 kilometers away. This data allows us to rewind the cosmic clock, tracing the paths of stars backward in time to see if they intersected with our sun's own journey billions of years ago. A star that was once gravitationally bound to our sun would have been flung away on a very specific trajectory when their bond was broken. By modeling these ancient gravitational interactions, astronomers can predict the kind of velocity and path an escaped twin would have, and then they can comb through Gaia's immense catalog looking for stars that match that predicted motion. It's a digital recreation of the solar system's birth cluster, allowing us to identify celestial cousins who once lived in our immediate neighborhood. But motion alone isn't enough. The galaxy is a vast and busy place, and many stars can have similar paths by pure coincidence. The true clincher in this cosmic identification parade is chemistry. This is where Gaia's other powerful capability comes into play: spectroscopy. As Gaia observes each star, it doesn't just measure its position. It also captures its light and splits it into a spectrum, revealing the dark absorption lines that act as a unique chemical barcode. Every star born from the same molecular cloud inherits an identical mix of elements, a specific ratio of iron to hydrogen, a particular abundance of silicon, and most tellingly, the same distinct signature of rare, oddball elements like europium and yttrium. The probability of two unrelated stars having the exact same chemical recipe across dozens of different elements is astronomically low. So, when Gaia finds a star that not only moves like it came from our sun's birth cluster, but also shares its precise chemical DNA, the confidence that we found a true sibling skyrockets. This dual-pronged approach, combining dynamics and chemistry, has already borne fruit. Researchers sifting through early Gaia data releases have identified a number of promising candidate siblings. One of the most exciting early candidates was a star known as HD 162806. Analysis showed it has a chemical composition that is a near-perfect match for our sun, and its motion, when projected backward, suggests it was in the same region of space as our sun billions of years ago. While it's not necessarily the sun's specific binary twin, it could be just another star from the same large cluster. Its discovery is a monumental proof of concept. It demonstrates that our sun's birth family is still out there and that we have the technological means to find them. Each new data release from Gaia provides a richer, more precise dataset, allowing scientists to refine their search and narrow down the list of candidates with ever greater accuracy. We are, in a very real sense, watching the first family reunion of our sun take shape in real time. The implications of successfully identifying the sun's lost twin would be profound, closing a cosmic loop that has been open for 4.5 billion years. It would transform the binary sun theory from a compelling model that explains orbital oddities into a confirmed historical fact. We would finally know with a high degree of certainty that our solar system's childhood was a dynamic binary affair. This wouldn't just be a footnote in an astronomy textbook, it would fundamentally reshape our understanding of planetary system formation. we could study this twin star in detail, analyzing its own planetary system, if it has one, and comparing it to our own. Is its system orderly or chaotic? Does it have a collection of strange, detached objects in its outer reaches? The comparative planetology would be breathtaking, offering a direct glimpse into how two systems, born from the same stuff, evolved down different paths after their violent separation. Ultimately, the search for the Sun's sibling is about more than just finding a missing star. It's about completing the origin story of our entire cosmic neighborhood. It's a quest to understand the initial conditions that led to the Earth forming where and how it did, to the Moon being created by a giant impact, and to the Oort cloud being stocked with comets. Every candidate star identified by Gaia is a piece of a puzzle that, when fully assembled, will show us a picture of our own beginnings that is far more dramatic and interconnected than we ever imagined. The quiet, solitary sun we see today may well be the survivor of a broken partnership, a single parent that raised a family of planets after its other half vanished into the galactic night. And with every new byte of data streaming down from the Gaia spacecraft, we get one step closer to finding the other parent and finally hearing the full story of our solar system's birth. But how do we move from a captivating idea to a tangible possibility? How can we test a theory about an event that occurred 4.5 billion years ago, one that left no direct physical evidence beyond its potential gravitational ghost? The answer lies not in telescopes but in silicon and code. In the quiet hum of supercomputers, astrophysicists are performing digital archaeology, constructing virtual models of our solar system's infancy and running the clock backward and forward to see if a second star truly fits into the picture. This process of scientific simulation is the rigorous backbone of the binary sun theory, transforming it from a fascinating story into a testable and potentially falsifiable modern scientific hypothesis. To understand the power of these simulations, think of them as the ultimate cosmic playground. You start with a digital sandbox, a virtual space governed by the unbreakable laws of gravity, just like our real universe. Into this space, you place a young sun and a protoplanetary disk of gas and dust, populated with millions of virtual planetesimals, the building blocks of planets. Then you introduce the crucial variable, a second star. You can adjust its mass, its initial orbit, its distance from the primary star. With all the parameters set, you press play. The simulation begins, and over millions of virtual years that pass in a matter of hours or days on the computer, you watch the drama unfold. You witness how the two stars waltz around each other, their gravitational fields intertwining to create a complex, shifting landscape of influence. You observe how this dance stirs the protoplanetary disk, nudging some planetesimals into new paths, flinging others out of the system entirely, and perhaps allowing a few to coalesce into planets in stable but unusual orbits. The true power of this method lies in its capacity for repetition. A single simulation run is just one possible story, one potential timeline, but the universe operates on probability. So, scientists don't run the simulation just once. They run it thousands, even millions of times. Each run, they slightly tweak the starting conditions, the mass of the companion star, the initial tilt of the disk, the density of the material. This technique, known as a parameter study, allows them to explore the entire range of plausible scenarios. They are essentially asking the computer, out of a million different ways our solar system could have started with two stars, in how many of those simulations does the final result look like the solar system we actually live in today? Do the virtual planets end up on orbits that resemble the strange, detached paths of Sedna and its kin? Does the process naturally produce a massive, spherical Oort cloud? And critically, does the model often lead to the ejection of the second star, leaving behind a single sun and a system of planets with the specific orbital quirks we observe? This is where the theory faces its most rigorous tests. A successful simulation isn't one that just creates a cool-looking binary system. It's one that reliably produces an outcome that is a statistical match for our reality. For instance, if a model consistently results in the inner terrestrial planets being destabilized and ejected whenever a second star is present, then that model would be a strong argument against the binary hypothesis for our own solar system. After all, we are here on Earth, so a model that makes our existence highly improbable is a model that likely doesn't reflect our history. Conversely, if a wide range of initial binary configurations consistently lead to a stable inner solar system and successfully reproduce the clustered orbits in the Kuiper belt, then the case for a binary past becomes significantly stronger. The simulations act as a filter, separating plausible narratives from physical impossibilities. Recent computational work has yielded some remarkably encouraging results. Sophisticated models have shown that a primordial binary companion, with a mass similar to the Sun's and orbiting at a distance of several hundred astronomical units, could indeed be the sculptor we've been looking for. These simulations demonstrate that such a star would be highly effective at capturing scattered planetesimals from the outer disk and placing them onto the very same strange, detached orbits we see with objects like Sedna. Furthermore, the gravitational interplay between the two stars can naturally explain the slight orbital tilts of the planets and even provide the gravitational kick needed to eject a hypothetical super-Earth. The simulations show that the departure of the companion star, whether through a close encounter with a passing sun or the gentle pull of galactic tides, then freezes this new architecture in place. What remains is a fossilized solar system, its outer reaches bearing the unmistakable imprint of a gravitational hand that is no longer there. Of course, this digital detective work also reveals the challenges and limitations of the theory. The simulations are only as good as the physics and the initial conditions we program into them. We still have uncertainties about the exact density and composition of the original protoplanetary disk, and the chaotic nature of gravitational interactions means that tiny changes can lead to wildly different outcomes. This inherent chaos is a double-edged sword. It allows for the dramatic events the theory requires, but it also means that pinpointing the exact parameters of the lost twin is incredibly difficult. The simulations can tell us that a binary past is plausible, even likely, but they cannot yet tell us with precision the exact mass and orbit of our Sun's former partner. That crucial piece of the puzzle may have to wait for the identification of a real stellar sibling through missions like Gaia, a discovery that would provide the ultimate reality check for these virtual recreations of our cosmic past. So we've gathered the clues that point to our Sun's long-lost companion, but the mystery only deepens when we ask the ultimate question: where did it go? The fate of this stellar sibling is not just a matter of celestial bookkeeping. It's a dramatic story written by the fundamental forces of the galaxy, a narrative of gravitational betrayal, cosmic capture, or perhaps a quiet, dark retirement in the cold depths of space. Each possible destiny paints a different picture of our solar system's past and its place in the wider cosmos, transforming a theoretical partner into a character in an epic galactic saga. One of the most compelling and scientifically probable fates is that the twin was violently evicted, cast out from our family to become a permanent wanderer. In the chaotic stellar nursery where our system was born, close encounters with other newborn stars were common. A passing star swinging too near our young binary pair could have engaged in a brief, intense gravitational tug-of-war. The mathematics of these three-body interactions are notoriously unstable, and the most frequent outcome is that the lightest member of the group gets slingshotted away at high speed. In this scenario, our Sun's companion received a gravitational kick so powerful it broke the bond with our Sun forever, catapulting it out into the galaxy to live out its existence as a rogue star. Picture this stellar castaway, a brilliant sun suddenly alone, drifting through the freezing, empty blackness between star systems. It would carry with it no warmth, no planets, no light beyond its own, a lonely beacon on an endless journey through the interstellar void. Billions of these rogue stars are now believed to roam the Milky Way, silent testaments to the violent gravitational dramas that shape star clusters in their youth. If this was our twin's fate, it is now an invisible exile, its light lost among the countless stars of the galactic disk, forever separated from the planetary family it helped create. But ejection is not the only possibility. Perhaps the encounter played out differently. Instead of being flung away into solitude, the companion could have been stolen. Imagine another star system, perhaps itself a binary, passing close to our own. The gravitational interplay in such a meeting is a complex dance, and one potential result is an exchange of partners. Our sun's twin could have been captured, its allegiance transferred from our sun to this new stellar group. It would have become a captured star, a permanent addition to another system, perhaps orbiting a new primary star in a wide, stable binary relationship. In this new home, it might even have its own family of planets, worlds that formed under the light of two suns that were both strangers to us. This idea transforms the narrative from one of lonely exile to one of cosmic adoption. The companion didn't vanish, it was inherited by another stellar family. Its influence would then have been redirected. Its gravitational might now shaping the architecture of an entirely different planetary system far across the galaxy. We could, in theory, search for such a system, a star with a strange, mismatched companion whose chemical fingerprint hints at an origin in a different stellar nursery, a celestial orphan that found a new home. Then there is the most elusive and haunting possibility that the companion never left at all. What if it wasn't a brilliant twin but a failed one? This theory suggests our sun's partner was a brown dwarf, an object often called a failed star. Brown dwarfs form like stars from collapsing clouds of gas, but they simply don't have enough mass to ignite sustained hydrogen fusion in their cores. They are cosmic in-betweeners, more massive than a planet like Jupiter, but not quite a true shining star. A brown dwarf companion would have been dim, emitting only a faint, deep red glow from the residual heat of its formation, cooling over billions of years into near total blackness. If it orbited far enough away in the frozen outer darkness of our solar system, it could have remained hidden from our telescopes all this time. This is the concept of a dark twin, a massive, hidden gravitational presence lurking in the periphery of our own backyard. While the original nemesis hypothesis of a Death Star has been largely ruled out, a colder, quieter brown dwarf is a different proposition altogether. It would be extraordinarily difficult to detect, a shadowy ghost whose presence might only be inferred through its subtle gravitational effects on the very same extreme trans-Neptunian objects that first sparked this entire investigation. Each of these destinies, the rogue, the captive, or the dark dwarf, carries its own profound implications. If the twin was ejected, its departure was a singular, violent event that froze the solar system into its current configuration. If it was captured, it represents a lasting connection between our solar system and another, a thread tying us to a distant, unknown stellar family. And if it remains as a cold, dark dwarf, it means our solar system is not what it seems. We are still a binary system, but one where the secondary is a dormant, almost invisible giant. The ongoing search for this lost sibling continues on all fronts. Astronomers scan data from infrared telescopes like the James Webb Space Telescope, which is perfectly suited to find the faint heat signature of a cool brown dwarf. They also continue to run sophisticated computer models, simulating millions of stellar encounters to better understand the most likely pathways for a binary breakup. And of course, the galactic archaeology of the Gaia mission continues to sift through the chemical and dynamical fingerprints of nearby stars, hoping to find one that is both a perfect match and on a trajectory consistent with an ancient escape or capture. The fate of our sun's twin is more than an astronomical cold case. It is a fundamental piece of our cosmic identity, a missing character whose story is inextricably linked to our own planet's genesis and the very possibility that we are here to tell the tale. This journey into our own potential binary past does more than just rewrite our local history. It fundamentally reshapes our search for life in the cosmos at large. For decades, the hunt for habitable worlds was instinctively focused on stars that look like our own solitary, stable, middle-aged G-type stars. The underlying, often unspoken, assumption was that a system like ours, with its single light source and orderly planetary orbits, provided the ideal, perhaps even the only, cradle for life. The discovery of exoplanets shattered that comfortable notion, revealing a staggering diversity of worlds in environments we once considered hostile, including binary star systems. And if our own Earth formed and thrived under two suns, even for a short time, then our planet becomes the ultimate case study, a living testament that life's requirements might be far more flexible than we ever imagined. Consider the real-world examples we've already found. Astronomers have identified planets in binary systems with evocative names like Kepler-16b, a world that orbits two stars, creating a permanent double sunset straight out of science fiction. Even more compelling are systems like Kepler-47, which hosts not just one, but multiple planets circling a pair of stars. These aren't just barren, scorched rocks. One of the planets in the Kepler-47 system orbits within the habitable zone, that Goldilocks region where temperatures could allow for liquid water to exist on its surface. The very existence of these worlds proves that stable, long-term orbits are possible in multi-star environments. This forces us to abandon the old idea that binary systems are inherently chaotic and destructive. Instead, we must view them as complex gravitational ecosystems with their own unique patterns of stability, where planets can find safe orbits around one star or around both for billions of years. The galaxy is filled with these dual sun systems, and if they can host planets in life-friendly orbits, then the cosmic real estate available for biology suddenly expands exponentially. This new perspective forces us to rethink the very definition of habitable. In a single star system, the habitable zone is a relatively simple, spherical shell surrounding the star. But in a binary system, the concept becomes dynamic and three-dimensional. The gravitational interplay between the two stars creates a constantly shifting energy landscape. A planet's climate wouldn't be governed by a single, steady rhythm, but by the complex interplay of two light sources. There might be periods of intense heating when the stars are close together in the sky from the planet's perspective, followed by more moderate temperatures when they are widely separated. This might sound like a recipe for climatic chaos, but life on Earth has proven to be remarkably resilient, adapting to everything from ice ages to tropical hothouses. Perhaps life on a binary world would evolve to be even more robust, with biological rhythms tied to the complex orbital periods of its two suns. The potential for seasons would be incredibly intricate, governed not by a single axial tilt, but by the combined effects of the planet's own tilt and the changing positions of its host stars. Life might flourish in ways we can barely conceive, with organisms that hibernate during the double summer, or become hyperactive during the unique light of a dual dawn. Our own solar system's potential history adds a profound layer to this exoplanet search. If Earth itself incubated life under two suns, then the conditions we consider standard for habitability are not a universal rule, but merely one successful pathway among many. This realization liberates the search for life from a narrow, sun-centric bias. We can now look at the multitude of binary systems in our galaxy not as cosmic oddities to be avoided, but as prime targets for investigation. The next generation of telescopes, like the James Webb Space Telescope and future ground-based observatories, will be able to analyze the atmospheres of planets in these systems. We can search for biosignatures, the chemical fingerprints of life, such as the simultaneous presence of oxygen and methane in worlds that experience two sunsets. Finding such evidence on a planet in a binary system would be a monumental discovery, confirming that life is not a fragile fluke confined to a specific, tranquil environment, but a robust and pervasive cosmic phenomenon capable of taking root in a stunning variety of stellar arrangements. Ultimately, this shifts the entire paradigm of astrobiology. We are moving away from a checklist of Earth-like conditions and toward a much broader understanding of planetary habitability. It's about identifying worlds with sufficient energy sources, chemical complexity, and environmental stability over geological timescales, regardless of whether that stability comes from one star or two. The ghost of our own second sun, therefore, serves as a powerful guide. It teaches us that our solar system's quiet present may be the calm after a more dynamic storm, and that the path to a living planet can be far more adventurous and varied than we ever suspected. As we continue to scan the heavens for signs of our celestial neighbors, we do so with a wider lens and a renewed sense of possibility, knowing that the conditions for life might be written not just in the light of single stars, but in the complex and beautiful gravitational dances of stellar pairs across the galaxy. Of course, any theory as grand and transformative as this one must be able to withstand the full force of scientific scrutiny. For this idea to move from a captivating possibility to a more established part of our cosmic history, it has to answer some very tough questions from the skeptical scientific community. The process of peer review and critical debate isn't a flaw in the system. It's the very engine that drives science forward, separating elegant stories from demonstrable truths. So, let's put on our skeptic's hat for a moment and examine the most compelling arguments against the binary sun theory. One of the most significant hurdles the theory faces is the simple yet powerful argument from statistics and probability. While it's true that most stars are born in binary systems, the type of system that best fits the evidence for our solar system is a specific one, a wide binary. And here's the catch: wide binaries are notoriously fragile. As we've discussed, they are highly susceptible to disruption from galactic tides and close encounters with other stars. The critics point out that for the binary model to work, our sun's companion had to stick around just long enough to sculpt the outer solar system, perhaps for a few 100 million years, and then be neatly removed, leaving behind a perfectly stable single-star system. This requires a very specific sequence of events. A companion forms, it influences planet formation, and then it gets stripped away at just the right time without causing catastrophic disruption to the inner planets. To some scientists, this begins to sound like a series of special circumstances, a narrative that relies on a fortunate chain of coincidences rather than a common, predictable outcome. The quieter, more conventional single-star formation model, they argue, while perhaps less dramatic, remains the more parsimonious explanation. It doesn't require this intricate stellar dance and subsequent cosmic divorce. This leads directly to the second major criticism, the problem of alternative explanations. The binary sun theory is often invoked to explain specific anomalies, like the clustered orbits of distant objects in the Kuiper belt. But skeptics rightly ask, is a second sun the only way to explain these quirks? The leading alternative, as we've touched on, is the existence of a large, undiscovered planet, the hypothetical Planet 9. This is a classic scientific standoff. Is the gravitational signature we're seeing the fossilized handprint of a star that left long ago? Or is it the ongoing, subtle tug of a massive world still lurking in the darkness? Proponents of Planet 9 have developed sophisticated models showing how a distant super-Earth could naturally shepherd these extreme trans-Neptunian objects into their clustered orbits. From this perspective, inventing an entire second star that has since vanished might be seen as an overly complex solution when a simpler, albeit still hypothetical, planet could do the job. The same principle applies to other solar system riddles. The tilt of the planet's orbits that could be the result of gravitational resonances during the early migration of the giant planets. The existence of the Oort cloud, perhaps it was built more gradually through the combined nudges of Jupiter and Saturn and the gentle pull of passing stars over billions of years. The criticism isn't that the binary theory is wrong, but that it isn't yet necessary. Many of the puzzles it seeks to solve can still be addressed with varying degrees of success within the standard single-star model. Perhaps the most fundamental challenge is the stark lack of direct, irrefutable evidence. In science, extraordinary claims require extraordinary evidence, and a second sun is certainly an extraordinary claim. At present, the evidence for the theory is entirely circumstantial. It's a collection of gravitational clues and computer models that are consistent with the idea, but not definitive proof. We have no photograph of this companion, no light signature from a nearby stellar sibling that we can definitively link back to our sun. The ghost is, for now, just a ghost. The ongoing search for solar siblings through missions like Gaia is heroic, but it is also a difficult and uncertain process. Even if we find a star with a matching chemical fingerprint, proving it was our sun's specific binary partner, rather than just another cousin from the same birth cluster, will be an immense challenge. We would need to match its chemistry, its age, its mass, and its trajectory in a way that is statistically undeniable. Until that day comes, critics can always fall back on the same powerful objection. It's a beautiful and intriguing story, but show me the star. What makes this debate so healthy and productive is that it forces the proponents of the binary theory to refine their ideas and make more testable predictions. A strong theory isn't one that has no criticisms, it's one that can respond to them with better data and more precise models. The response to the statistical argument, for example, is to run ever more sophisticated simulations to determine just how likely it was for a wide binary to persist for the required amount of time in our sun's specific birth environment. The answer to the Planet 9 alternative is to find more extreme trans-Neptunian objects and see if their orbital patterns match the predictions of the binary model more closely than those of the planetary model. And the quest for direct evidence continues unabated, with every new stellar catalog offering a fresh chance to find the missing piece. This back and forth is the sound of science working as it should. It prevents us from falling in love with a captivating idea simply because it's romantic or mind-expanding. It demands rigor. The binary sun theory is not yet a consensus, and it may never be. But by engaging directly with its toughest critics, it evolves, becoming a more robust and scientifically valuable proposition. Whether it is ultimately proven true or serves as a brilliant stepping stone to a deeper, even more surprising understanding of our origins. That search for our sun's lost sibling is accelerating at a breathtaking pace, driven by a new generation of astronomical observatories that are fundamentally redefining what is possible to see and measure in the cosmos. We are no longer limited to simply watching the sky. We are now beginning to conduct a galactic-scale forensic investigation, and the tools for this investigation are unlike anything that has come before. At the forefront of this new era are two revolutionary instruments, the James Webb Space Telescope and the Vera-C Rubin Observatory. Each possesses a unique and complementary set of powers, and together they are poised to hunt for the ghost of our second sun with a precision that was pure science fiction just a decade ago. The James Webb Space Telescope, or JWST, represents a quantum leap in our ability to analyze the very essence of starlight. Its primary strength lies in the infrared part of the spectrum, the realm of heat. While our eyes and traditional telescopes see the visible light that stars emit, JWST is designed to see the faint thermal glow of cooler, dimmer objects. This makes it the perfect instrument for hunting one specific type of potential twin, a cold, dark brown dwarf. If our sun's companion was a failed star that never truly ignited, it has been cooling for billions of years, emitting only a feeble infrared signature. Previous surveys could easily have missed such a faint, cool object, especially if it is lurking in the distant reaches of our own solar system. JWST, with its colossal, gold-plated mirror and exquisitely sensitive infrared detectors, is conducting deep, high-resolution surveys of the sky, capable of picking up the heat signature of a Jupiter-sized object at immense distances. It's like turning on a thermal spotlight in a dark room where we've only ever used a flickering candle. If there is a dark twin still orbiting our sun, JWST is our best bet for finally illuminating it. But JWST power extends far beyond just detecting faint objects. Its spectroscopic capabilities are its true superpower. When it observes a star, it doesn't just capture its image, it dissects its light with incredible detail, reading the chemical barcode of that star's atmosphere with a fidelity that was previously impossible. This is crucial for confirming solar siblings identified by the Gaia mission. Gaia provides a fantastic first-pass chemical analysis, but JWST can perform a deep-level DNA test. It can measure the abundances of specific isotopes, different forms of the same element, and trace molecules that are virtually invisible to other telescopes. If Gaia flags a star as a potential sibling, JWST can be pointed at it to confirm the match with an almost undeniable level of certainty. It can determine if that star not only shares our sun's general composition, but also its exact isotopic ratios, the equivalent of confirming two individuals share not just the same eye color, but the same unique pattern of freckles. This will allow astronomers to separate true, intimate siblings from more distant cousins in the sun's birth family, dramatically narrowing the search for the specific binary partner. While JWST acts as a precision scalpel for detailed stellar analysis, the Vera-C, Rubin Observatory operates as a colossal net, trawling the entire visible sky with relentless efficiency. Currently under construction in Chile, this facility is designed for one primary purpose: to conduct the legacy survey of space and time, or LSST. This is arguably the most ambitious movie of the universe ever attempted. Over the course of a decade, its enormous 3.2 billion pixel camera will photograph the entire available sky every few nights, creating a time-lapse of the cosmos on an unprecedented scale. The volume of data will be staggering, cataloging tens of billions of objects from nearby asteroids to the most distant galaxies. For the search for our solar twin, the Rubin Observatory's power is its ability to detect motion. It will find things simply because they move. This makes it the ultimate tool for finding the subtle, telltale movements of a dim, distant object within our own solar system. Whether it's the hypothetical planet 9 or the even more elusive brown dwarf twin, the Rubin Observatory will see it. By comparing images taken nights apart, its powerful software will identify any object that has shifted its position against the backdrop of fixed stars. It is expected to discover millions of new trans-Neptunian objects, mapping the outer solar system in more detail than we ever thought possible. This flood of new data on the orbits of these distant ice dwarfs will provide a critical test for both the Planet 9 and the binary star hypotheses. The specific patterns of orbital clustering and their inclinations will be revealed with statistical power that current data can only dream of. The observatory's data will either reveal the gravitational shepherd to be a planet, or it will show that the orbital patterns are truly fossilized, perfectly consistent with the ancient and sudden removal of a second sun, with no massive planet required to explain them. The synergy between these two titans of astronomy is what makes the next decade so promising. The Rubin Observatory will perform the ultimate census of our cosmic backyard, flagging countless faint, moving objects for further study. JWST will then follow up on the most intriguing of these candidates, using its infrared eyes to determine their composition, size, and temperature. This 1-2 punch could, in a single observing cycle, identify a distant, massive object and confirm whether it is an icy planet or a warm, failed star. Beyond our own solar system, this powerful combination will also accelerate the search for solar siblings. The Rubin Observatory's vast survey will help refine the proper motions of billions of stars, improving our models of stellar trajectories, while JWST provides the definitive chemical analysis to confirm their lineage. We are standing at the threshold of a new era of discovery, an era where a question that has lived in the realm of theory and simulation can be answered with hard, observational evidence. The tools now at our disposal are not just incremental improvements, they are transformative. They grant us the sensitivity to see the faintest of cosmic embers and the comprehensive vision to watch the entire sky in motion. The ghost of a second sun, which has until now been a specter inferred from gravitational wrinkles and ancient myths, is about to face the most rigorous search in history. Whether the outcome is a confirmed discovery or a definitive refutation, we are poised to close a 4.5 billion-year-old chapter in our solar system's history, finally learning the truth about the family our sun was born into and whether we once truly lived under the light of twin dawns. Picture our world not as a lone child of a solitary star, but as a member of a bustling stellar family, a world that came of age in a cosmic metropolis. For generations, humanity has looked up at the quiet, predictable sun in our sky and woven a narrative of celestial solitude. We've framed our planet's history as a singular, almost isolated journey around a single, steady light. This perspective has shaped our understanding of our own significance, placing us in a serene, orderly system that feels almost designed for our existence. But if the theory of a lost twin is correct, that entire worldview is fundamentally upended. Our cosmic home transforms from a quiet suburb into a place with a much more dramatic and interconnected biography, a story written not in solitude but in partnership and subsequent loss. Imagine stepping outside on a clear day 4.5 billion years ago. The sky above you would be an utterly alien vista. Instead of one brilliant disk, two suns would hang in the heavens. Their light would blend, casting not one but two distinct, overlapping shadows from every rock and tree. The quality of the light itself would be different, perhaps a deeper, more golden hue. Days would have a different rhythm, governed by the complex orbital dance of the twin stars. There would be periods of double daylight where the landscape is bathed in an intense, almost surreal illumination, and other times when one sun has set and the other hangs low on the horizon, creating a prolonged, eerie twilight. The very concept of night would be transformed. Instead of the profound darkness we know, the night might be perpetually lit by the second, cooler sun, a constant companion in the sky that banishes true darkness and paints the clouds in perpetual, muted colors. This wasn't a science fiction landscape. It could have been the genuine cradle of our planet, the environment in which the first oceans formed and the first self-replicating molecules stirred to life. This shift in perspective forces us to reconsider Earth's entire gravitational history. Our planet didn't form in a placid, predictable gravitational field. It was forged in the crucible of a dynamic, binary gravity well. The gentle, rhythmic tug we feel from our moon today would have been just one part of a far more complex symphony of forces. The young Earth would have felt the persistent, rhythmic pull of the second sun, a massive body whose gravity would have subtly influenced everything from the sloshing of our magma oceans to the very rate of our planet's spin. This dynamic environment might have been the driving force behind some of the most violent and formative events in our planet's youth. The giant impact that created the moon, for instance, moves from being a random, freak accident to a much more probable occurrence in a system where two stars were constantly stirring the pot of planetary debris. Our planet's axial tilt, that crucial 23.5-degree lean that gives us our seasons, may not be a random leftover from its formation, but a specific outcome of gravitational interactions with its stellar sibling. The very conditions that make Earth so habitable today might be the direct legacy of that early, chaotic binary environment. This new narrative challenges the deep-seated human tendency to see our story as a solitary one. We are storytellers, and we often frame our existence as a linear journey. But the binary theory reframes Earth's biography from a solo voyage into an epic ensemble piece. We were not a lone child of a lone star. We were part of a stellar partnership, a binary pair that for a time defined our entire celestial neighborhood. Our sun had a companion, a true sibling, and the planets were the children of that union. This makes our solar system story one of family, interaction, and even separation. The departure of the twin star becomes a kind of cosmic coming-of-age story, a traumatic event that forced our system to mature and find its own independent stability. The quiet, orderly solar system we see today isn't the default state. It's the calm after the storm, the settled adulthood after a turbulent and dramatic youth spent within a dynamic stellar family. The philosophical implications ripple outwards, touching our search for meaning and our place in the grand scheme. If our own solar system's peaceful present is the result of such a dynamic past, then what does that say about the universe at large? It suggests that stability and order are not the cosmic default, but are often hard-won achievements, the result of complex processes and even loss. It paints a picture of a universe that is fundamentally interactive, where stars and planetary systems are not isolated islands, but are constantly influencing one another through gravitational encounters and galactic tides. Our existence on this pale blue dot becomes even more remarkable when viewed through this lens. We are not the products of a serene, inevitable progression in a quiet corner of the galaxy. We are the survivors of a more chaotic and dramatic history, a history that included a stellar twin whose gravitational hand helped mold our world into a habitable home before it vanished into the galactic night. This realization doesn't diminish our significance, it deepens it, connecting our story irrevocably to the wider, dynamic, and ever-changing tapestry of the Milky Way. So as we bring this cosmic journey to a close, let's gather together all the compelling threads we followed. The evidence for a second sun isn't a single, undeniable photograph. It's a tapestry woven from multiple, independent lines of inquiry, each one strengthening the others. We began with the very architecture of our solar system, where the strange, clustered orbits of distant worlds like Sedna defy easy explanation without some immense, external gravitational influence in the distant past. We looked at the sheer existence and spherical shape of the Oort cloud, a structure that a single star struggles to build but a binary pair could construct with ease. We even found echoes in our own planet's biography, from the violence of the late heavy bombardment to the very existence of our moon, events that become far more probable in the chaotic gravitational environment of a young binary system. These scientific puzzles are given a profound human dimension by the persistent myths from cultures across the globe. Stories of a second sun that brought both light and chaos, and of a celestial archer who restored order to the heavens. While not proof, these legends resonate powerfully with the scientific narrative, suggesting a shared memory of a sky that was once fundamentally different. And now, in the 21st century, we have the power of supercomputers, where millions of simulations demonstrate that a binary past is not just possible, but a remarkably elegant solution that ties all these loose ends together into a coherent and compelling whole. It explains the odd, the unexplained, and the anomalous features of our cosmic neighborhood with a single, elegant premise: our sun was not always alone. It is crucial to remember that this is not yet a proven fact. The binary sun theory remains a legitimate and powerful scientific hypothesis, one that is still being tested and debated. Yet its greatest strength is its ability to solve multiple, seemingly unrelated puzzles with one elegant framework. It provides a unified explanation for the architecture of our outer solar system, the formation of our cometary cloud, and the violent history of our inner planets. It reframes our solar system from a quiet, orderly suburb into a place with a dramatic and dynamic history of partnership and loss. The quiet, predictable system we see today may well be the calm after a spectacular stellar storm, the settled adulthood that followed a turbulent youth. This idea fundamentally changes the way we see our place in the cosmos. It connects our story irrevocably to the wider galaxy, reminding us that our solar system is not an isolated island, but a product of dynamic interactions, a celestial drama of gravitational forces, close encounters, and perhaps a long-lost sibling. The next time you find yourself on a clear day, take a moment to look up at the sun. Feel its familiar warmth on your skin, and then, for just a second, try to picture another brilliant disk sharing that blue expanse. Consider the possibility that our sun's light is not the only one that has ever fallen upon this world, that the very conditions that allowed life to flourish here might have been shaped by a twin whose gravitational hand helped mold our home before it vanished into the galactic night. The ghost of that second sun invites us to see our history not as a solitary journey, but as an epic ensemble piece, a story with a missing character whose absence has shaped everything we know. We want to hear what you think about this incredible possibility. Does the evidence convince you? Do you have your own theories about our solar system's wild past? Share your thoughts and wonders in the comments below. The conversation about our cosmic origin